Okay, so we've seen how to differentiate a lot of different functions. All of these functions on the left-hand side. So we know how to differentiate now something that looks like x to the power of n, or ax to the power of n, or a constant, remember, differentiates to give us 0. We know how to differentiate the three trigonometric functions, sin x, cos x, tan x. And in the last few videos, we've been looking at differentiating inverse trigonometric functions, so functions that look like cos inverse x over a, or sin inverse x over a, or tan inverse x over a. Now we're going to have a look at another type of functions which are called exponential functions. So exponential functions all involve this number e. So what is that number e? Well, let's have a look if you just remember. So we have a look at this. I think you should be able to read. So the number e is a famous irrational number and is one of the most important numbers in mathematics. So e is an irrational number, and the first few digits of e are 2.718. You can read that yourself. And it's often called Euler's number after a famous mathematician called Leonhard Euler. So it's a very, very famous number. It's given the symbol e. So anytime you see the number or the letter e in maths, it's the number 2.718. Okay, so we're going to look at differentiating functions that have this number, this irrational number e in them. And it's very simple. If we have a function that goes f of x is equal to e to the power of x, then when we differentiate that, we just get e to the power of x. So e to the power of x differentiates to give itself. And then e to the power of ax differentiates to give ae to the power of ax. So I'll put up a video about why e to the power of x differentiates to give itself. It's a very simple proof. We can do it by first principles and show that when we differentiate e to the power of x, we get e to the power of x. But for the moment, if we just have a look at these again, so remember that e to the power of x differentiates to give e to the power of x, and e to the power of ax, where a is a constant, just some number, it could be a half, it could be 2, it could be minus 3, differentiates to give us ae to the power of ax. So let's have a look at a few examples of differentiating trigonometric functions, and it's pretty simple. So we want to differentiate the following functions with respect to x. So the first one is e to the power of 3x, then e to the power of minus 5x, and then the third one e to the power of x squared. So let's look at the first one. So we have f of x is first. So f of x is equal to e to the power of 3x, and we want to differentiate that. So f dash x, just by going with the rules, well, we know that e to the power of ax differentiates to give us ae to the power of ax. So our function is e to the power of 3x. So there's a 3 where there's an a. So we will differentiate to give us 3e to the power of 3x. So we get f dash x is equal to 3e to the power of 3x. And that's it. Very, very, very simple. Second one, we're differentiating e to the power of minus 5x. So e to the power of minus 5x. So let's call that function g of x. So then g dash x, again, just to differentiate e to the power of minus 5x, instead of an a here, we have minus 5. So e to the power of minus 5x differentiates to give us minus 5 times e to the power of minus 5x. So we get, when we differentiate, g dash x is minus 5 e to the power of minus 5x. So again, very, very simple. The third one is a little bit harder, but it's still not particularly hard. So we're going to have to use the chain rule, because we have the function, let's call it h of x is equal to e to the power of x squared. So we have this function e to the power of x squared. Now that doesn't quite look like either of these. This is e to the power of x, this is e to the power of a times x, but we've got e to the power of x squared. So we've got two functions. Our first function is the x squared part, and our second function is the e to the power of that part. So we're going to have to use the chain rule on this one. Chain rule. So to use the chain rule, we're going to go separate it out into our two functions. So our first function, let's call, I don't know, let's call I of x. Doesn't make any differences. So I of x is equal to x squared, and let's call the second function j of x. Why not? So j of x will be equal to I of x, this function, all to be squared. So we have, no it's not, sorry, what am I doing? So we have the second, so okay, let's start again. So we have h of x is equal to e to the power of x squared. We have our two functions. The first function is x squared. So we have I of x is equal to x squared, and our second function, let's call it j of x, is equal to e to the power of I of x. So e to the power of our first function. So here we can differentiate the function I dash x will be equal to, well, differentiate x squared, and we know we get 2x, and differentiate e to the power of something, well, we can just use this function down here. So j dash x is equal to e to the power, when we differentiate e to the power of one thing, like e to the power of ix, we just get e to the power of ix. So e to the power of ix, which is, instead of writing ix, the function, I can write what ix is x squared. So when we differentiate I of x, we get 2x, and when we differentiate j of x, we get e to the power of x squared. And by the chain rule, we know that h dash x is equal to these two functions multiplied. So it's equal to I of x times j dash x, I dash x times j dash x, which is 2x. So it'll be 2x multiplied by e to the power of x squared, and that's it. So what do we do? So we differentiated this part, differentiate x squared, and we get 2x. Differentiate the whole thing, so differentiate e to the power of that, and we get just e to the power of x squared, and then we multiply those two functions together, and we get this. So again, just very, very simple using these two functions. Let's have a look at one more example of differentiating an exponential function. So we want to differentiate this time e to the power of x times x squared. So the first thing you should notice is that we've got a product. So we're going to use the product rule on this. And if you remember, the product rule says if f of x is equal to u of x times v of x, then f dash x, if you can remember this, go back to the video on the product rule. So f dash x will equal v of x times u dash x plus u of x times v dash x. So we've got u of x is the first part of the product and v of x is the second part. So in this function here we have u of x is equal to the first part. So we've got e to the power of x times x squared. So u of x will be e to the power of x, and v of x will be x squared. So u dash x, well, differentiate e to the power of x. You come back to the previous page. So when we differentiate e to the power of x, we just get e to the power of x. So that's very straightforward. Oops, pages are all over the place here. So u dash x will be just e to the power of x, and v dash x, well, we've differentiated x squared loads of times at this stage. So when we differentiate x squared using the x to the power of n rule, we just get 2x. And then by the product rule, f dash x will equal v of x, so x squared, times u dash x, so times e to the power of x, plus u of x, so e to the power of x, times v dash x, so times 2x. So here's our answer. We can tidy that up by, if you look, we can factorize out e to the power of x. So that'll be the same as e to the power of x times x squared plus 2x. It's just a little bit tidier to write it like this.